Hello, it's Stat 135, Lecture 23. Last time I gave an intro to section 9.5, where we had a box with two types of tickets, say a 0-1 box, 0 with probability P1 and 1 with probability P2. P1 plus P2 is 1. We draw n tickets with replacement, and we form an observed and expected table. Our observed table is following a binomial distribution, and because x1 and x2 are binomial, np1 or np2, we know that the expectation of E1 is NP1 and the expectation of E2 is NP2. So those are the expected values. And we're testing a hypothesis where the null is that the binomial cell probabilities P1, that the binomial cell probabilities in your box are P1 and P2. And the alternative is that you have some other binomial cell probabilities. Then we looked at a chi-square test statistic that was equivalent to chi-squared with 1 degree of freedom. Today we're going to continue our intro, generalizing from binomial to multinomial cell probabilities, P1 to PM. And then actually start section 9.5 called the generalized likelihood ratio test for the multinomial distribution. So multinomial random variable, it's a sum of n independent m outcome cells or random variables. And so we have P1 is a probability of outcome 1 and so on. P1 to PM is 1. So what's the chance of getting x1 outcome 1, x2 outcome 2, and so on, where the sum of the xi's is n? So the answer is given by the multinomial formula. So multinomial formula. So this is the generalization of the binomial formula. If we know P1 to PM, the multinomial distribution is said to be completely specified. In other words, we can actually get a number when we calculate this. So in n trials, then we get observed and expected cells, just like before, where now x1 to xm are given by a multinomial distribution. So then just as before, we have this sum of observed minus expected squared over expected for each cell, which converges to a chi-squared with m minus 1 degrees of freedom. So I'll just move on here. So we lightly looked at, in section 8.1, an example of a chi-squared situation here, where we modeled the arrivals of these alpha particles in 10-second intervals as a Poisson process, where lambda was 10 arrivals per lambda was something that we needed to estimate. So I'm not sure why I put this here. But in any case, I'll just say with Poisson process. And so you can imagine here that we have a box with tickets 1 to 17 here, and actually I'm a little confused here. There are only 16, so I think I will start this with P2. So so we have tickets with these probabilities, and we're drawing we draw 1,207 of these tickets, and what we're getting here is in our observed column here are the number of observations. So for example, we got 28 intervals out of the 1,207 where there were 3 arrivals. 56 intervals had 4 arrivals. So these x1, or let's call it x2 to x17, these are following a multinomial distribution where the p's are actually given by a Poisson distribution. So the p's being Poisson, there was a parameter mu that which is the average number of arrivals per 10 seconds that is unknown, so we first had to estimate it, and we did estimate it, and it was 8.4 arrivals per 10 seconds, and that allowed us to use the Poisson formula then to calculate the pk, or probabilities here. So to get the expected column here, it was just NP. So each these xi's are binomial NP, NPK, and PK is given by my Poisson formula. So I was able to compute the expected column, and then we can look at a chi-square test statistic to see how close the observed and expected counts are. This is a test of how good our model is, and that will follow a chi-square distribution. So it's actually going to be 16 minus 1 minus another 1 degrees of freedom. 16 minus 1 is because our sample space is 16 dimensional. So we have P2 out to P17. Those are free parameters, except that when you add them, it has to be 1, so you lose 1 degree of freedom there. So it's 16 minus 1. And then minus 1 is because it's the dimension of the null space. The null space, so the null space is one dimensional because our null is that our null box is following a Poisson. The probabilities in our null box are Poisson, which have a single parameter. So that single parameter needed to be estimated. We subtract 1. Okay, so much for an intro. Now on to likelihood ratio test. So we have a categorical variable here, unlike in chapter 11 when we had a continuous variable. And so our null box has probabilities P1 theta, P2 theta, and so we're drawing with replacement size n. We have an observed table here. So let's say that right, we're assuming here that that we have 3 different outcomes, and so step 1 is going to be to estimating our parameter theta. So that is if your null probability distribution isn't completely specified. Step two, we're going to do a goodness of fit test. So we need to find an expected table, and we write our null and alternative hypotheses. And flashing forward, minus 2 log lambda. So this lambda here is the generalized likelihood ratio, and we saw in section 9.4 that asymptotically this is a chi-squared with dimension the dimension of the parameter space minus the dimension of the null space, which in this case is the number of cells minus 1 minus the number of estimated parameters. And this minus 2 log lambda, we'll see next time, it can be closely approximated by this Pearson chi-squared statistic. So here's a good example to understand. It's called the Hardy-Weinberg equilibrium model. So we have a null box now instead of, let's say, Poisson. We have some other probabilities that are dependent on a single parameter theta. Notice that the probabilities add up to 1, and so that's our null box. We observe, let's say, the counts shown here. Step 1, we need to find an MLE, and we do that. I'll sort of just skip through these details. So once we find the MLE, we can find the parameters, the probabilities, and hence find the expected counts that we should get. And so our null is that we have multinomial given by the Hardy-Weinberg, and the alternative is that we have some other multinomial distribution. I've rewritten the observed and expected counts. You do a chi-squared goodness of fit test, and we got a very small chi-squared, which means that we're not going to reject the null. We're actually going to accept the null. It's a good match. So next time we will do the theory behind the goodness of fit test. I wish you all a very great evening.